publication that I came across was of elliptic curve cryptography. Can anyone tell me what any of those words mean? No? Okay, you know, I know you know. Julia?
Isn't cryptography when you have like a text and you change the words or the letters into something different?
Yes, very good. If you've seen any movies about the subject, there's a lot of them where you get a message, you put it into something that is unreadable, and then someone else gets it, and then they can read it. It's not magic. Turns out it's math. So, elliptic curve cryptography, I will explain what each of those words means later. My supervisor was Professor Rehovot. That's my email, but Facebook is honestly better. Okay, so the first question, what is an elliptic curve? Here is a little graph for you. For the physicists, think of the letter ohm and just turn it on its side. That's a very good description of what most elliptic curves look like. This is the equation. You have, what's interesting about it is that you have something of degree 2 on the left side and something of degree 3 on the right side. So it's kind of like a hybrid between hyperbola and parabola. Do not confuse an elliptic curve with an ellipse, which is something you might have learned in high school geometry or calculus. Very, very different. You can see, first of all, it looks different. And second of all, if that wasn't enough for you, the formula looks extremely different. As Anna mentioned, algebraic geometry is the study of zeros or the roots of polynomial equations. If the equations are different, you're most likely not going to end up with the same roots. So as far as algebraic geometry is concerned, those are two very different things. A and B are constants, y and x are variables. Now, is that the only type of elliptic curve? Do they all look like that? No. Here are some examples. So you can see a progression of what an elliptic curve looks like. For all the biologists out there, this is very similar to when you have something like mitosis and you have something splitting off. It's a very similar process. The formulas are listed on the top. Unless you're a genius, there's no way the formula should be able to tell you how to visualize the graph. So you're just going to have to take my word on this that those formulas correspond to those pictures. However, they might look different, but they all still possess the same symmetrical properties. Because the parts that we care about is we care about the two symmetric tail thingies that are going out here, and we care about the origin, which is on the left. Here's some more pictures. This is what elliptic curves look like on a sphere. It's a very pretty picture. You might have that on a marble in your house. Also, turns out an elliptic curve is actually equivalent to a donut. Sorry, our coffee break is over, but I thought I'd put that in there. It helps you understand that once these two things merge together, it still follows the shape. And on the field of complex numbers on a projective plane, you end up with a donut, or for people who actually know what the word means, a torus. And for all the chemists here, this is a spectral diagram of a progression in color of all the curves. So if you put them all on one diagram, you will see that it's still all very, very related, even though the pictures might look different. So why do we care? Yeah, they're pretty pictures, but for all of you applied people out there, that's not enough, as I was told. So you see a couple more pictures, but this time you're seeing several points, because a pretty picture is not that good if we can't do anything with it. So we label some points, and we're capable of doing some computations on those points. So what's special about elliptic curves? First of all, they're symmetrical. And you can see the symmetry, the horizontal symmetry, which, yes, appears in a lot of objects. However, this is a lot less symmetrical on all sides than, let's say, a sphere. So it's or a sphere or a circle or something that has more than one symmetry. So the symmetry allows us to do computations like this, where you have two different things and then you have the same number corresponding on both sides of the curve. What else? It's an algebraic variety. What the hell is an algebraic variety? Not going into very detailed mathematics because I promised some friends that I wouldn't bore them to death. An algebraic variety is, what does variety mean? Come on, it's not enough.
Different things.
Different things, yes. An algebraic variety is when you have some algebra, so some algebraic equation. The variety is the set of all solutions of that algebraic equation. So when we say that this is an algebraic variety, you have some type of curve, which is the set of solutions to a certain equation. And it turns out that the elliptic curve is actually one of the most simple examples of algebraic varieties. Addition is defined. Did you know that you can add geometrically? That's a thing. So you can add on elliptic curves. What else? And it's a commutative group. Commutative is related to the fact that it's very symmetrical, so it doesn't matter in which order you do things, as long as it's with respect to the horizontal symmetry. Now, I mentioned that you can add. We can add geometrically? Yes, that's a thing. So here are some examples of different ways that you might want to add on an elliptic curve. So one of the foundational properties you have is that when you have a straight line, you're going to have to be, the points of the straight line are going to all have to be equal to 0. Conservation, whatever theorem in your field of science, conservation of mass, whatever, they're all the same. If you're adding the same point, the point will end up being tangent to the curve. So as you can see over here, p plus q, or p plus q plus 0, because this is not in this direction, it's in this direction. And then you have just a tangent line, which is going to be p plus 0. Or you can simply just do a tangent line on this side of the curve, and it's just going to be 2 points instead of 3. Here's a little GIF that's supposed to play. Oh yeah, it plays. That plays. That's nice. That shows you kind of how the line shifts depending on which points you pick. So this is a in more detailed diagram. So yes, we can add this way, but conventionally we put this letter as -r because we want to end up with a solution that is not a negative number, because we don't really like putting minus signs. We mathematicians are lazy. So we have p plus q plus -r equals 0, and if you still remember some math from like high school, you should be able to put the r from the left side of the equation into the right, and you'll end up with p plus q equals r. And that's how you add on elliptic curves. Here's, so this is a little diagram of how the addition works. So you add two things, you project it, and this is your answer. And you can do this process over many times, and each time you're going to end up with a different point on the elliptic curve. Does that work? There we go. So this is a little bit different. If you've ever played games like Brick Breaker on your phone, that was like 10 years ago. I don't know if you ever came across that, but this is when you only take the whole numbers. As Anne explained, on different fields, some elements become invisible, and so you're only able to see some parts of the graph. So over here, two interesting things that I'd like to point out is that first of all, you get random points that look nothing like what you've seen of elliptic curves so far, yet it is still an elliptic curve. And second of all, because it's so differently spread out, you end up with a wrapping of the diagram. So it starts here, it goes here, and then it finishes up there. But it's the same exact process that you're seeing over here and that you're seeing over here. Next word in the title. I'm just defining the title for now. What is cryptography? Yeah, that's a little meme. So you might have seen some type of like code or cipher. That's something you play around with when you're little. The biggest advance in the field of cryptography was made about 50 years ago when people discovered that you don't actually need to share a secret key in order to encrypt and decrypt something. The whole foundation of public key encryption is that when you have some text message that you want to send, you don't need to have a private key to encrypt it, but you do need to have a private key to decrypt it. And so the whole point of this is if you live in very shady neighborhoods, you might want to have a lock not with one key, but with two keys. And in this case, you end up having two keys. You have one public key that you don't care who knows or who sees, but you have your second private key that is unique only to you. And the combination of the two forms your digital signature. This is a really great diagram that I like to use to illustrate what cryptography is. So let's say we have Alice and we have Bob. They both start with some colored common paint. Now they each choose their secret color. Alice likes red, Bob likes green. And when they combine the two, you see I added a little bit of chemistry, you get a mixture of this color. which are both different. Then Alice and Bob, they have a meeting, they go to a coffee shop, they exchange their little different colored mixtures, and then each of them proceeds to add their own color again. And because of, this should be very obvious, they both end up with the same common secret. Now, you could be like, well, I'm a chemist, I can separate colors, come on. That's not necessarily true. This is simply an analogy. You're assuming that it's easy to mix colors. It's not that easy to take a mixture of colors and separate it to something that would be identical to the ones already, things that you already had. And this is the foundation of encryption. And so the elliptic curve Diffie-Hellman is one of the first elliptic curve cryptography things that was invented. You have different letters. Those are for the mathematicians that can read letters instead of numbers. You have a private key and you have a public key. And you have a secret key. And the combination of the three is giving you the common secret that both of them use. Okay, so I'm Alice. So I'm going to take the part of Alice. Who wants to be Bob? You want to be Bob? I can trust you to multiply numbers, right? Okay, so pick a number from 1 to 10. And do not tell me. Okay, and I'm going to pick a number from 1 to 10 too. Great. Now, we can both decide on some common number. Let's say 7. So, in your head, multiply your private number by the public number that we just decided. Tell me what you got. 42. Okay. I got 21. Now, I'm giving you 21, and you're giving me 42. And then you multiply that by your number again. You got it? What did you get? Future mathematician, ladies and gentlemen. Yes, that's exactly what I got too. So via this process, you understand that you will come to a shared secret, even though neither of us has said out loud our numbers. And yes, we can all divide, but pretend that you're multiplying two very large prime numbers by each other. You can multiply, but if you don't know one of the original prime numbers, it's going to be nearly impossible for you to factor the super large number into the original two prime numbers. So this is very cool. Now, of course, this is math, and we like giving cool names to everything. This is called the trapdoor function, and there's a little diagram in case you don't know what a trapdoor is. Trapdoor function is when you have something that is easy to do, but it's not so easy to undo. And the foundation of public key cryptography was based on the fact that it's really easy to multiply numbers and raise numbers to exponents, but it's not so easy to take these large numbers and figure out what they were based on. These are just some various diagrams to represent the process. And actually, yes, Alice and Bob is a classic in computer science. If you know those two names, any cryptologist will think you're totally fitting in. Here, this is a meme that's the dream of all cryptographists. Here's an example. If you have some function on some letter y that is a product or some operation done to x and y, given fxy, it's difficult to find either x and y unless you know x. And so x is the secret key that you need for decryption, but you don't necessarily need to know how x works to multiply the two numbers. So I've explained the foundations of how cryptography works and how cryptography works and what elliptic curves are. So now comes the question of what is ECC, how is it used, and why do we care about elliptic curve cryptography? So after RSA was invented, about in like the 1970s by some scientists from MIT, shout out to the MIT people over there, because that's where apparently all of the math was done. Nothing much has been done since then, and ECC was created in about the 1985s, and it was a great idea because the key sizes were a lot smaller. And what does that mean for people who don't understand key sizes and bits? It means that you're using smaller pieces of information. Think about doing, let's say, a puzzle. It's a lot easier to make a puzzle if you have less pieces and if you have smaller pieces than if you have gigantic pieces and you have lots of them. So first of all this, and second of all, because the key sizes are smaller, you don't need that much internet storage and you don't need that much generating power in order to be able to encrypt and decrypt processes. And here are some numbers for comparison. The most common elliptic curve are P256 and P384. And comparatively, this is a lot bigger. Yes, there we go. Now, things you might have heard in the news regarding this. I'm sure some of you have heard the name of Edward Snowden, aka the guy who took a bunch of NSA information, decided to go to the news and was like, yeah, so the NSA is listening in on a bunch of your stuff. You should probably know about this. And the reason why, and I didn't know this until this particular project when I started looking into elliptic curve cryptography, is because you can't come up with two random large prime numbers, right? Because it's hard enough memorizing the ones up until 100. So then NSA came up with a random number generator, so you wouldn't have to do that yourself. And so it will give you your secret key. And hypothetically, they should know what the secret key is. However, the beauty of this is that they installed something called a backdoor in elliptic curve cryptography on everything any encryption algorithm that was done in the United States. And so what that means is that the NSA basically has access to your secret key, which means they can access your encrypted data. This is not particularly great, and so that's why people tend to start reverting back to RSA once this happened, because they know that RSA is a trusted algorithm. Yes, it might be a bit more bulky, but they know that it works. And however, elliptic curve cryptography still remains to be one of the most efficient encryption algorithms, at least until we get into post-quantum ways. And this meme over here explains why specifically elliptic curve cryptography is so great, is because it uses something called the discrete logarithm problem. Mathematics has advanced enough where we can write programs in supercomputers and quantum computers which make factoring easier. This problem, 30 years later, still absolutely no progressions as to how to solve it. It's incredibly difficult. And what this showcases is that it's probably unsolved, not because it's that difficult, but because no one cares. Creds to Jordan on that quote. There we go. Here's some of the sources. The National Institute of Standards and Technology. They have a lot of the information, and they're the ones that distribute everything that the NSA does. National Security Agency, they'd probably kill me if I didn't put this in the slide. Wikipedia, because that's all that we as students use. Something that my supervisor recommended. It was a great text that was in way more mathematical depth than what I gave you a brief overview of here. This is a great website if you want to read up on computer stuff and you don't know much about computer science. And of course, the Weizmann Institute of Science. Acknowledgements, huge thanks to Professor Rehovot, who shared his knowledge of elliptic curves with me from the mathematical side. Professor Tsigan, who was my professor who wrote me a letter of recommendation so that I could be here. Professor Vanderboom for having this amazing program, the Weizmann Institute, and